Okay, I'm going to do one more example of this, and I think then see if you guys have questions, and then you'll have almost an hour if you wanted to spend working on homework, getting caught up. Please do. It's good for you. This will be good for getting through the class, so it's nice. Okay, so let's see. So suppose here's the function f x y or equals the square root of x squared plus y. And what is this function at 2.95 and 7.1 equals what? So you could plug that in your calculator and you could get an answer. You could get it to a pretty decent approximation. I think this is good to linearize this. First of all, it's what you're supposed to do in this section, but it'll be nice to have this nice linearized form. So we need the partial derivatives of this thing. So maybe I should rewrite it first as the 1/2 power x squared plus y to 1/2. Then my partial derivative with respect to x will be 1/2 x squared plus y to the negative 1/2. And then I got to do a chain rule here to get 2x. So clean it up a little bit. I guess that's x on the top, the 'two's cancel, and I'd have the square root of x squared plus y in the denominator. Similarly, the y derivative, df dy, you do the exact same thing, except you think of x squared as being constant. So you'll get 1/2 x squared plus y to the negative 1/2. Then you multiply by the derivative of the inside, but now it's 1. So this is sort of similar. We get 1 over the square root of x squared plus y. So if we want to know what the answer to this is, then the idea is we compute the function at 3, 7 to start with, and then we use x equals 3, y equals 7 as my start points. But how much does x change by and how much does y change by in order to get to the point that I want to get to? So y is going from 7 to 7.1, so my y will be, my delta y will be 0.1. X is changing from 3 to 2.95, so it's actually going down negative, so the delta x is negative 0.05. So I use all of this to calculate df or dz. We'll just use df. There's no z's in here right now. So this is the total differential, which will be the partial derivatives multiplied by their respective deltas. So let's see. So we will get that df is the partial derivative with respect to x over x squared plus y times delta x. I think the book after a while just says we're just going to use dx, and you know what I mean, I guess. I'll try and just keep it like this for right now. And then 1 over x plus y times delta y. And then I just sub all these values in for to calculate what it is for this particular example. So what happens if I stick in 3, and 7 into, well, what do I get if I plug it into my original equation? So if I plug in 3, this will become 9 plus 7, so that's 16, and that's under the square root. So I get square root of 16 or just 4. So I know that the answer is going to be close to 4, but is it bigger than 4, less than 4? How close to 4? Well, the df tells me how far off from 4 that I am. So if I plug in x equals 3 and y equals 7 into this whole thing, well, this will be 3/4, and this will be 1/4, because I'm plugging in x equals 3, y equals 7, and I'll get square root of 16 now in the denominator of my df, and the top would be 3 and 4. So then I multiply these by negative 0.05 and 0.1, and that's pretty, I think it's a pretty easy calculation to see that this is, well, let's see. We get multiply out negative 0.15 over 4 and 0.1 over 4. So we get negative 0.05 over 4. Divide by 4. If I did it right, I think it's, is it 0.025? No, that would be half of it. Not doing the calculation right here. 0.0, what does that equal? I did this all right. 3, 4. Well, I'm going to just use my calculator. No, I'm not going to use my calculator. That's dumb. So 5/4 is 1.25. So move the decimal place over twice, 0.25. So negative 0.125. So that means that my final answer up here, the approximation would just be 4 minus 0.0125. So 3.9725. 9, do that. 3.9775. Yeah, 3.9875. Shouldn't do too much in my head. Assuming I did it right, I think I might have made a small error in there, but that's pretty close. So that's the process. Find the total differential, plug in the points for the x and y that are near the, that are actually the whole numbers that you can calculate. Figure out how far off you are from each one. Those get multiplied on, and then in the end, this delta here is how much your function approximately changes, and calculate that out. How good is the approximation? Well, we're not going to do any error analysis on this. So, well, if it's this, then if these are off by a factor of blah, then the overall should be within a certain factor as well. We're just going to say that for right now, approximate. So, anyway, I think that's probably the best place to stop for right now. And again, ask if you guys have any questions on anything that we can handle that came up in the last hour. The silence is deafening. I'm staring at 2 people on camera, and I'm staring at another like a dozen black screens, maybe 3. So I'll assume you're there. Every time I log off, there's still one person that's still there, and I'm like, I'm sure you know the acronym AFK. So anyway, go work on the homework. I'll see you this afternoon. We'll cover a good bit of ground this afternoon, but otherwise, free time to go work. So have a good rest of your morning.
Thank you, sir.
Thank you, sir.